There are several monosaccharides that are important to mention. Now, all of these monosaccharides, you don't have to know their structure because you already have the table and you can get the structures from there. So you don't have to memorize any of those structures there. But just know that riboses and deoxyriboses, these we use them in RNA and DNA synthesis. So if you look at the ribose and the deoxyribose, the only difference in them is in the second carbon in there. Okay, for the ribose, the second carbon does have an OH. For the deoxyribose, the second carbon is not a chiral center. This one is a chiral center. This one is not. And it does have two hydrogens instead. So this is why we call it a dioxy, because it has two hydrogens in there. Glucose, it's a hexose. It is the most nutritionally important monosaccharide. It is considered to be a blood sugar, and whenever it is consumed, it enters the liver, and the liver converts it into glycogen, which is energy. Glucose is used as a sweetener in there, and you can find the structure of glucose in the table in there. Glucose exists as a pyranose, and this is the structure of the pyranose. And again, once you know the Fisher projection of glucose, you can simply change that into a pyranose. You don't even have to memorize anything, you guys. So that is going to be the OH, and that is going to be the CH2OH. What I drew now is the beta D glucose. Okay. For the galactose, it's again a hexose. It's very similar in structure to glucose, and it is one of the components of the disaccharide lactose that we will discuss as we proceed. So this is the Fisher projection of the D-galactose, and you can easily cyclize that. So let's go ahead and draw its cycle in there. I'm drawing the beta anomer. This is going to be the OH. The OH over here, you do have the OH and the CH2OH, and that is the structure of the beta D galactose. This is the Howarth structure of the beta D galactose. Fructose, these are ketohexoses. These are the sweetest monosaccharides. These are the fruit sugars in there. And you can cyclize fructose into furanoses or pyranoses. So you can also cyclize into pyranose. Pyranoses are more stable and they exist more than furanoses in there. So that is regarding the monosaccharides. So disaccharides, these are two monosaccharide units. And these monosaccharide units, we link them together by an acetyl or a ketyl glycosidic linkage. An example of a disaccharide is maltose. Maltose is made up of a reaction of two glucose units. Okay, so the reaction always starts from carbon number 1, which is the anomeric carbon of the first monosaccharide, and carbon number 4. Okay, so if I'm starting here from 1, that is going to be 2, 3, and 4, and carbon number 4 of the second monosaccharide in there. This is the reaction. This is how it happens, and this is how the two glucose units, they bond with each other between carbon 1 and carbon 4. Carbon number 1 loses its OH, and carbon number 4 loses its hydrogen in there. So you are going to form a bond between carbon 1, the oxygen that is left on 4 in there. So that is the bond between 1 and 4. And we're going to call it a glycosidic linkage. So that is going to be the oxygen there between carbon 1 and carbon 4. That glycosidic linkage is formed from the alpha glucose, right? So it formed from the alpha. This is carbon number 1 and the OH was down. So this is why when I want to name that glycosidic linkage, it formed from the alpha glucose, then it's going to be an alpha. And I am making a bond between carbon 1 and carbon 4. So this is how I name it, alpha 1,4 glycosidic linkage. Okay, so this is the linkage. This is how you name it in there. Now, if you look at carbon number 1 over here in the maltose, this is the maltose structure, and this is when the two glucose units, they combine with each other. So if you look at the maltose, and this is how you can check and see if the disaccharides are reducing sugar. So we said that all monosaccharides are reducing sugars. Now for disaccharides, not all of them are reducing sugars. You have to pay attention. To know if they are reducing sugars, you always look at carbon number 1 in there of the disaccharide and see. If you have it as a hemiacetal, so this means that there's an OH in there, then this means that this is a reducing sugar. If it was an OR, then no, it's not a reducing sugar. It cannot be oxidized further. But since this one is an OH, it can be oxidized further, so this is a reducing sugar. So maltose is considered to be a reducing sugar because it is a hemiacetal and it has an OH in there. Okay, so again, whenever you want to name a glycosidic linkage, always the glycosidic linkage is going to follow the orientation of the OH on carbon number 1. So if it is on the alpha, then you're going to start your naming from the alpha. If it is beta, then it's going to be beta in there. And then you've made a bond between carbon 1 and carbon 4, so just go ahead and name that as such. Maltose is a malt sugar. It is 2 glucose units. They are joined by an alpha 1,4 glycosidic linkage, and it is formed during the digestion of the starch to glucose. It is a hemiacetal. It is a reducing sugar in there. So this is the explanation why maltose is a reducing sugar, because I can easily oxidize the maltose in there, and I can break the hemiacetal. I can break the hemiacetal and turn the OH in there into an aldehyde. So this is why maltose is a reducing sugar. Another disaccharide is lactose. Lactose is milk sugar, which is composed of a combination of 2 monosaccharides, a galactose and a glucose unit. The galactose is B is the beta anomer, and the glucose is the alpha anomer. As it is written, the reaction starts from the beta galactose, so this is the anomeric carbon. Your OH was pointed up, so this is why you are forming the glycosidic linkage that is pointed up. You are reacting carbon number 1, so carbon number 1 there is going to lose its OH. Carbon number 4 is going to lose its hydrogen, and you are going to form your glycosidic linkage this way there. So if you look at lactose, as I said last time, you look at lactose and you look at this carbon over here. This is the anomeric carbon of the glucose unit. If it is a hemiacetal like this one, this means that lactose is a reducing sugar. And it is a hemiacetal because this carbon is connected to an OR and this is an OH. This means that upon oxidation, we can break this bond and the alcohol is going to turn into an aldehyde. Sucrose is a disaccharide, is another disaccharide. Sucrose is the regular table sugar that we use, and sucrose is composed of 2 monosaccharide units. fructose and the glucose units. And the fructose and the glucose, so this is the fructose unit and the glucose unit, these are joined together by alpha 1 beta 1 glycosidic linkage. So your glucose in there, this is going to be carbon number 1, and that is going to be an alpha D glucose unit. So this is why its OH is pointed down in there. And then the beta D fructose unit, its OH is pointed up. So that fructose will lose a hydrogen, the glucose will lose an OH. Those two are going to be combined together, and this is going to be the structure of sucrose. Guys, you are not responsible to draw the structure of sucrose. All what you need to know is that sucrose is made up of fructose and the glucose units, and these are joined together by an alpha 1 and beta 2 glycosidic linkage. Sucrose, as you can see in here, if you look at both anomeric carbon, if you look at this carbon over there, it is an acid. It is actually it is a ketal. It's not an acetal. So this carbon over here is actually a ketal group. Why it's a ketal group? Because take a look, let's highlight. This is a COR and the CO and an R in there. So that is a ketal group. So there is no way that this can be oxidized further. This means that sucrose is not a reducing sugar. So lactose is a reducing sugar. Maltose is a reducing sugar. But sucrose is not a reducing sugar in there. Polysaccharides. So polysaccharides, these are condensation polymers. These contain thousands of monosaccharides units that are connected together. And because of that long carbon chain or long polymer chain, we can say, because these are polymers, these are completely water not soluble. Even though they have a lot of hydroxy functional groups in there, but these hydroxy functional groups, they become hydrated, but they are not enough to dissolve the polymer in there. So that polymer is not water soluble. What they do instead, they do form thick colloidal dispersions when heated in water. An example of that, starch. So this is why starch is used as a thickener in sauces and in gravies. Starch is not water soluble. It does not dissolve in water. Instead of dissolving in water because of all of these OHs in there, it does form a thick colloidal dispersion. Okay. If you look at the properties of polysaccharides, these have, because they are polymers, these have very high molecular weight. They actually they are tasteless. They have no taste in there compared to monosaccharides and disaccharides. Monosaccharides and disaccharides, they are sweet. These are smaller molecules compared to polysaccharides. Disaccharides and monosaccharides are water soluble, but polysaccharides, they are insoluble. They do form colloidal dispersions in water. Okay, monosaccharides and disaccharides, all monosaccharides and some disaccharides, those they are reducing sugars. In there, of course, with the exception of sucrose. Sucrose is not a reducing sugar, but polysaccharides, these are not reducing sugars. Polysaccharides, they have negative test with the Benedict solution. An example of polysaccharides, we have two examples of polysaccharides. We have starches and we have cellulose. So a starch is simply a polymer, and that polymer is X number or thousands of units of glucose units that are connected with each other in there. The glucose unit is a D-glucose unit, and starch is a major storage form of D-glucose in plants. It is made up of a glycosidic linkage. It's an alpha 1 for a glycosidic linkage of glucose units from 1,000 to 2,000 glucose units that are connected to each other. So we're going to put all of these glucose units next to each other. Always the reaction is going to start from the anomeric carbon of one glucose unit to carbon number 4 of the second glucose unit in there. Since it's an alpha 1,4, then the OH is going to be pointed down, so the glycosidic linkage has to be pointed down in this case. The last polysaccharide is cellulose. Cellulose is made up of glucose polymer units that are connected to each other. The connection is different from the starch. The starch connection is the alpha 1,4 glycosidic linkage between glucose units. However, for the cellulose, the connection is going to be between the beta 1,4 glycosidic linkage in there. This is a linear polymer. It is an amylose. Amylose is a simple polysaccharide, which is made up of glucose units that are connected to each other. So we can say that starch is an amylose, and cellulose is also an amylose as well. Cellulose is the most abundant organic compound on Earth, and it is found in plant cell wall. So what you need to know, guys, is the composition of cellulose, what it is made up of. It is made up of a beta 1,4 glycosidic linkage in there. So if I give you the structure of the glucose in there, you are able to connect those glucose together in the same format in order to get the structure of cellulose.